All right, we can begin. Any questions from last time? Okay, so I want to continue our discussion of this two-point correlation function, and we'll mainly discuss it in K-space. And so we want to state, what does it actually look like? What is the spectrum of fluctuations? And then we're coming towards thinking about what on earth might have set up the spectrum in the first place. And that will take us to discussing the very early universe in the remaining lectures. Okay, so recall we have this two-point correlation function. C. And it's only a function of the distance between the 2 points. Is just this distance. Okay, and as we said, if the fluctuations are Gaussian, the 2-point tells you everything. There's nothing else you need to specify. So then if in K-space, we like to, we can just Fourier transform this thing. And so let me write it xc of r. I'll write it implicitly in terms of its own Fourier transform. Okay, and there we have the power spectrum. Okay, so I transform, or if you like, I've handed you the inverse transform. They just go back and forth between each other. Okay. And just as xc only depends on the magnitude r, p only depends on the magnitude of k. That's why I didn't write k vector. I just wrote k like that. Right? So k just means this in this argument. Okay, so these integrals, first of all, the angular part of this integral has to be simple because there's only an angular dependence here. There's no angular dependence there. Okay, so if you haven't seen that type of manipulation before, you could just write this as integral dk k squared, I don't know, sine theta, where let's say theta is the angle of k with respect to r. That's just the usual Jacobian. I guess I should have some extra, I don't know, d theta, d phi. And then I could write this as e to the I k r cos theta, p of k. Is that all right? Theta just measured relative to r. And then the angular integral here is an elementary integral because sine theta is proportional to the derivative of cosine. So we can do this integral. And the integral over phi is trivial. Just get a factor of 2 pi. And I dropped my 2 pi cubes. Okay, so if you do that, you get a 4 pi, 2 pi cubed, integral over k. And this integral just gives you a sine kr over kr p. Is everyone okay with that? You can check if r was 0, right? This is just 1. So the angular integral just has to give you 4 pi. There's the 4 pi. And if r goes to 0, this ratio of sine k over k goes to 1. That has a nice limit as r goes to 0. It approaches 1. Okay, so this is the one where we can write the correlation function as a one-dimensional integral over p. Any questions about this? People seen having to do those kind of integrals before? The angular bit is simple. You get this sine function showing up. Okay, let's just rewrite it very slightly. I'm going to, this is a factor here of 1 over 2 pi squared. My integral over k, I'm going to sneak in an extra factor of k over here. Instead of writing k squared from the Jacobian, I'm going to write k cubed. And then I have to compensate by writing dk over k. I can do that. But this, if you like, is d log k. Okay, so let's just write that as d log k. And then this sine function. All right. So I write it this way because I want to say something about how we can think about fluctuations on some scale r, how we might picture them in k-space. Okay. So this measure here is a good measure. It's just a log measure, right? So you just want to know the dimensionless measure, right? It's just some log. So you might want to know what's the contribution from some k to, e times that k. So this is more or less flat on that scale. Does that make sense? And if you're interested in scale r, its sort of primary contributions, right, should come from, you can imagine k sort of order 1 over r. Right? Certainly high k is not going to contribute much because then this factor here will be very small. Right? So naturally, if you're interested in physics on some scale r, you're thinking about wavelengths on that order or wave numbers that are inversely related to that. Okay? So in this regime where k is order 1 over r, this factor here is not too far from 1. If you were to literally set k equals to 1 over r as an example, the denominator would be 1, you'd have sine of 1, which is whatever that is, 0.7 or whatever that number is. Right? So this is some order 1 number. And then this is really the factor here that I've highlighted for you. Okay? So if you like, the kind of variant, a sort of a dimensionless variance on scale k is this thing. K cubed P of k. And we can even put in the 2 pi's that make it an extra good estimate. But I'm just highlighting that factor. I can do that. Whatever words I wrap around it is a separate story. And we sometimes call this delta, capital delta of k. Or we could call this thing sigma k squared. We can think of it as a kind of variance, a standard deviation. But this is dimensionless now. Okay? Delta is the density contrast, fractional density contrast. So C is dimensionless. In general, the power spectrum is not dimensionless. You see, it has to have units of volume, so that volume times k cubed is dimensionless. And once again, volume times k cubed is dimensionless. So this is a dimensionless measure of the fluctuations on scale k. Okay. So this is the kind of number, actually, when earlier I was saying, let's estimate things as starting off at 10 to the minus 4. What I actually had in mind is that that particular number is about 10 to the minus 4. That's sort of the precise statement. But these are statistical statements. So the statistical statement is if you pick a mode k, its Fourier amplitude has a standard deviation that's like this. Well, the standard deviation, the square root of that. Okay, so it will be of this order, but of course it could be a bit smaller, it could be a bit bigger. It's just a standard deviation. It could be positive, could be negative. Fourier coefficients don't have to be positive. And half of them will be positive, half will be negative. Okay, there are questions about this. So we want to talk about the shape of this thing, actually. Is everyone okay with its meaning? We could literally just talk about the Fourier transform, but then we'd be carrying around this dimension-full quantity. This is a much better measure of the size of the fluctuations on a scale of interest. Okay, so now I want to say something about the observations. Okay, we're gonna plot this thing in 1 minute, but let me state the observations in a slightly abstract way, and then we'll make it more concrete. Okay. So let me tell you, the observations have a very simple character to them. Okay, so there's a simple way of stating a kind of a rule that every K mode is obeying. And this rule is surprisingly simple. Okay? Is that when a mode K, let's say the physical K, K over A, the physical wave number, matches Hubble, H, which is itself a function of time. So this is also a function of time. Okay, we'll draw a picture in a minute. There'll be a special moment in the history of the universe where those two things match, depending on your choice of K. Okay, usually it'll be half the universe. Before that, one will be smaller than the other, and otherwise it'll be the other way around. We'll draw a picture. There's a special moment at which they match. And at that moment, the fluctuations are scale invariant, meaning they don't care what K that was. So the specific value, I'll take a square root of this thing, the square root of delta. Yeah, let's say delta of K at this special value. I don't know, we could call it K star. The special value where this happens is about 0.5 times 10 to the minus 4. That's the 10 to the minus 4 I've been stating again and again. Okay, so this is the value when K over A equals H. I don't really need this star. Okay, or sigma sub K. So somehow, and we have to do some work observations to deduce that, but let me state it in a simpler way possible. When the specific mode happens to equal H, it always seems to have an amplitude of fluctuations, a standard deviation that's more or less the same number, irrespective of K. Okay, so a bit of a mouthful. Let me try to flesh this out. Does anyone have a rough idea as to what I'm saying at this point? Okay. Let's flesh that out, and then we can use that to draw this curve. We have to do a bit of work to go from there to there. We have to use some information that we've been developing in the last couple of lectures. Okay, so what does this really mean? Right, so the two things we have to track is that the physical wave number, which goes like K over A, that depends on time, and then the Hubble parameter depends on time, as we know. Okay, so we have to look at both and see when do they somehow match. So maybe for the moment, let's look at lengths up this way and time this way. Okay, and let's just remember that lambda physical, the wavelength, is this 2 pi over K physical, and the Hubble length is, well, C over H. Okay. So I'm going to talk about it in terms of length, okay? But it'll be the same story if you want to plot K and H. All right. So let's plot the Hubble scale for the moment. Okay. So let's squeeze it in here somewhere. Okay. So what do we know about Hubble? How does Hubble depend on time? Let's say in the radiation era or the matter era. Let's focus on that. Don't worry so much about the dark energy era. Like who can recall what's H of T, and pick whatever era you want, say the matter era or the radiation era. Well, let's remind you. Let's say we're in radiation. A is proportional to T to the 1/2, the radiation, right? And A is proportional to T to the 2/3 in matter. Okay. So if I look at the physical wavelength, let's maybe we can start with that one. The physical wavelength stretches with the universe, right? So the physical wavelength is always proportional to the scale factor. So physical wavelengths grow, right? The universe stretches as t to the half in that era, and the physical wavelength grows as t to the 2/3 in the matter era. Is that all right? So that covers the first 10 billion years of the universe. Let's not worry about the last couple of billion where dark energy changes the equations a bit. Now, I also want to add to this thing Hubble. Okay, let's squeeze it in here maybe. Hubble is, well, A dot over A. So Hubble is 1 over 2t in the radiation era. And Hubble is 2 over 3t in the matter era. Okay? So the Hubble length, therefore, which is just the inverse of this, let's not worry about it, we set c to 1. The Hubble length, the inverse, would then be 2t. And then 3 over 2t. Okay, so that's all we need to know. So our Hubble length is growing in time. There's some 2 and 3 halves. Those prefactors are not going to matter much for this discussion. They're growing with t. Whilst wavelengths are growing with some other powers. They're growing with a t to the half and a t to the 2/3. So what's important, these halves and 2/3 matter. It's a smaller exponent than here you have t to the 1. Okay, so that's what matters. All right. So let's start with the Hubble length. Okay, think of this as a log-log scale. So let's call this one BH. It's, well, this could be in a linear scale. It's literally linear in t. Okay. Now I want to draw these things for you. And so a wavelength, let's say, I can have different wavelengths, small wavelengths, long wavelengths. And then this is how they depend on time. This is how they stretch. So a relatively small wavelength may do this, let's say. Just because this power here, a half or 2/3, doesn't matter too much, is less than 1. Okay, so at late times, it has to be less than this linear curve. And at early times, it's going to cross and be on the other side. Okay, this is for some value, I don't know, lambda 1. Say co-moving lambda. Does that make sense? So you give me a lambda in the early universe, and then that's how it stretches. There can be some other mode that initially has a bigger lambda. There'll be a whole spectrum, as it were, of modes. So I cannot just draw one line. I should have many lines. There'll be another one that does this, and another one that does that, and so on. Okay, so you lay it all down at some initial moment, and they go like this. So you see there are these special points, like here. This is the special point at which that mode has a wavelength that matches the Hubble length. Okay? And that's basically what I mean here. That's the statement where they're matching. Okay? You can argue about factors of 2 pi. When you go from k to lambda, there's a 2 pi. This turns out to be the more precise statement, actually, when you say it in k space. K equals h, which means lambda would be 2 pi times the Hubble length. Let's not worry about the 2 pi's for this discussion, okay? Pretend 2 pi equals 1. You get what I'm saying? So for my pictures. So this is when lambda equals Hubble length, which means k equals Hubble. So that's the special moment for that particular mode. And then there's another special moment for this mode, which we could call lambda 2 or lambda 3. Right? This would be 2 pi over k1, 2 pi over k2, so or equivalently for different values of k. And I'm going to mark on this thing here, let's say t equality, right? 47,000 years. So if I was being precise, my blue curve should have a little bend to them when they cross this line, because you go from the radiation era to the matter era. So I should really transition from a t to the half to a t to the 2/3. So I should put a little kink in these lines. Okay, but qualitatively it's like this. Is everyone okay with that? Okay, so the statement is for this particular mode here, as its wavelength matches the Hubble length, its typical amplitude of that mode is 0.5 times 10 to the minus 4. That's my statement. And for this mode, it happens to have 0.5 times 10 to the minus 4 at this moment, and so on. So these modes here, so this is a kind of interesting thing that will be sort of a theme of today's lecture. We're going back, let's say, to the very early universe. So we go back to the very early universe, everything's getting small, but we have to worry about small compared to what? Okay, so we go to the early universe, the Hubble length gets very small, the wavelengths of things get small, but you notice there's a certain sense in which the wavelengths are big, as it were, quote unquote big. They're big in the sense that they're actually bigger than the Hubble length, even though in meters they're small, right? On a log scale, think about all this. Okay, so this is a big deal. So in that sense, over here, when the blue part is above, in the early universe, when they're above this, these modes are huge in a sense. They're bigger than the Hubble length. We say they are outside the horizon. Okay. So on this side, outside the horizon. And over here, you are inside the horizon. Over here, let me draw another picture of this. Okay, so we'll call inside, I don't know, I, and outside, outside O and inside I. So just to be clear, I mean in region O, let's say the Hubble, let's say that's our Hubble volume. It's very small in the very early universe. Okay, maybe I should color code it. I could draw it in black. I guess I'm using black for the Hubble length. That's our Hubble volume. And over here, I'd be considering a particular mode whose wavelength is somehow bigger than that. So its wavelength somehow looks like this. Big mode. And then at later times, right, when we're inside the horizon, I have to draw both of these much bigger. This one they're all expanding. This one has expanded so much. Let's say it looks like this. This is now our Hubble volume. And the blue curve has stretched, okay? So I don't know. Let's accept that wavelength is bigger than that blue over there, right? Maybe I drew it too much. Something like this. The blue has stretched, but it didn't stretch enough. So it actually came inside the Hubble length. Now, in terms of our equations of structure formation, remember we were kind of doing a somewhat Newtonian analysis, okay? That kind of analysis is valid when modes are inside the horizon. So we've been doing a good analysis of how delta evolves with time here. Our equations apply there. This delta double dot plus 2h delta dot, etc. applies here. We've never really handled this case, where the wavelength is so big, it's bigger than the Hubble length. That really requires general relativity to do properly, okay? And we'll sort of touch on that in the next couple of lectures. But I just want to state for you something I did state already last time, is that in this case, the mode, its amplitude is frozen. Okay, in this case, the amplitude, according to the differential equations we write down, grows, right? Grows logarithmically in the radiation era, linearly in the matter era. Okay, let's say for the dark matter. And then there's this special point, this red point, where these two scales, my blue wavelength and my Hubble length, basically match. Okay? And that's the point at which the typical amplitude is 10 to the minus 4, and then it grows from there. Okay? Does everyone get it, what it means now? Questions about this funny picture? Yeah. Yeah, so the scale invariant here is the statement that this amplitude of fluctuation, there's no k in this formula here. So literally the amplitude is this 10 to the minus 4 laid down with this slightly awkward way of stating when it was laid down. But at that moment when it was laid down, they're always 10 to the minus 4. And it doesn't care if the k is 100 inverse megaparsecs or 10 inverse megaparsecs or 1 inverse megaparsecs, whatever the k is, they always have that amplitude of 10 to the minus 4. So you could easily have imagined that here there was some, there was a function of k living here. But there doesn't seem to be. Actually, stated more precisely, well, there's actually a very slight dependence on k that I'm not getting into right now. But it's almost scale invariant, let's say. Is that okay? All right. So from this, we can try to draw a picture as to what our fluctuations, which start off with this very simple statement, that's when they enter the horizon, we say, at those red dots. How does it evolve from that point onwards? It's going to evolve in a way that's different because modes are entering at different moments in time. So in particular, you think of this as going up in lambda, right? So a relatively short wavelength mode enters early, enters our horizon. A longer wavelength modes, they enter late. Okay. So an extreme version of this would be you could have a mode whose wavelength is today's Hubble length. That would be a gigantic one. Well, it's by definition entering today. Okay, so that would be, I could also draw a curve like this, where anyway, let's say it matches, I don't know, like this or something. These two curves could match at, say, today. That would be a gigantic wavelength whose wavelength is, 15 billion light years. Okay, so that's an extremely big mode. And the statement there would be if that's just entering today, its amplitude is 10 to the minus 4. Full stop. I don't have to do any further analysis. I don't have to say, well, it entered at 10 to the minus 4, which say this mode. This has an amplitude of 10 to the minus 4. But now I have to evolve for all this time to figure out what it's today. It's going to grow as it enters the horizon. It's going to grow because it's in this phase. So for these other modes, we have to do a bit of thinking as to what their value is today. This mode would be super easy. It's 10 to the minus 4. Okay. So other questions before we try to figure out what this implies? All right. So we want to use our knowledge of how things grow from the last couple of lectures. Okay, so here's our time. And we're going to be plotting these deltas. Okay, and I'm going to mark, I have to mark T equality. Here, T equality really matters because growth was logarithmic in the radiation era. And then it was power law, was linear. So that matters a lot for this curve. We can't forget about that. Okay, so let me put on this thing. First thing I'll do is a mode that we highlighted just for the sake of argument. I randomly considered a mode that started its life at 1 second. That was our silly example. And what I should really put here is an amplitude of 10 to the minus 4. Okay, 10 to the minus 4 times 0.5 would be the standard deviation. Okay, I don't know, divide by 2, doesn't matter much. Okay, so this is the mode that we described. And so it grows like a logarithm, and then it grows linearly. And then today it flatlines a little bit due to dark energy. Okay, so this is today. So that's that mode, let's say. So you could imagine that that's a mode that's rather short wavelength. Okay, so we could ask, what is the wavelength back here? So what I mean by this, if I'm laying it down at that moment, its wavelength at that moment was the Hubble length at that moment. If the universe was a second old, its Hubble length was about a second, right? There's some a factor of 2 there. So I guess it would literally be, the Hubble length would be 2 seconds, okay? So when the universe was 1 second old, the Hubble length was 2 seconds, right? So that was its wavelength back then, up to some 2 pi, order a second. You get what I'm saying? It got laid down at this 10 to the minus 4, and then it evolves because it's inside the horizon according to the formulas we laid down. Okay, so you might imagine that's, say, this one. Now let's try to draw this one. This one enters the horizon later, has a bigger wavelength, right? Wavelength is bigger, enters later. So this one here, let's say, here it starts off at 10 to the minus 4. That's the statement of scale invariance. So at some later time, maybe when the universe was, I don't know, 10,000 years old, whatever you like, right? It now starts its life at 10 to the minus 4 amplitude. That's the scale invariance. So I drew the dot at the same height. And now I should grow logarithmically to there, and then I should grow linearly. Okay? So the final amplitude it has today, you see, is a bit reduced. It's not reduced a massive amount because it only suffered a bit of log growth. Maybe I've exaggerated it here, right? Because this is only a log. I think of the whole thing on a log scale. I don't know. A bit hard to draw. But it suffered a little bit of log, but it got all the linear growth. So this number here maybe is only a little bit less than that number. That makes sense? Okay, and you can keep on going. I could even draw, let's say there's a slightly special one here that happens to do 2 things at once. It has horizon crossing at matter radiation equality. That's a special mode that does that. Okay, so that's a mode that starts its life at 10 to the minus 4 here, and then its whole life is just linear growth until it hits the dark energy era. Okay? So you see, again, we have reduction, but all these curves differ by some log. And then you could consider, say, this mode here. This mode enters the horizon even later, even longer wavelength. So it starts its life in the matter era. You see, this is the matter era. So that one would be, say, here. And so it just grows logarithmically. Okay. I didn't draw it very well, but you want to imagine that this is a big gap because it missed a whole pile of linear growth. Does that make sense? So this is somehow a big, let's say, gap. And this is small log, missed out on the gap size, and so forth. And then we could even go all the way to this mode here that happens to enter the horizon today because its wavelength is this Hubble length today. And that's a gigantic mode. So it starts at 10 to the minus 4, and that's it. It started today. I don't have to draw anything. Is that okay? And so you can imagine drawing all these various curves and, connect the dots on all of them. So let's say you drew 1,000 of those curves, and then you just report on the 1,000 outputs. Okay, and then we collect the 1,000 outputs, and then I want to draw a new plot with the 1,000 outputs. Does that make sense? We want to know what is the amplitude today. This is today. Okay, so this scale invariance gets transformed by growth into something a little bit complicated. So, okay, so I want to plot for you then the fluctuation. I could call it delta, but if you like, I could also just call this sigma, right? This is the standard deviation. The delta is just drawn from a distribution with that standard deviation. I'm really plotting for you the standard deviation. Yeah. This one here. We're not so good at doing that because it's so big that we can't really measure that one very well. We're only good at looking like subsections of the universe and then piecing it together. So actually this one, we're not when I say the data tells us this picture works, we're not totally sure that it's right down there, because we're not good at looking at the whole universe. But these modes we can check pretty well. Okay, so I want to plot this now. So now I'm going to be plotting at today only. I only care about the final result. Okay, and I'm plotting it versus K. Okay, which is, if you like, K physical over today. Today's value is 1, so that's just K. Okay. I literally want to plot for you the standard deviation today, which all started its life at 10 to the minus 4, but now has been morphed into a more complicated distribution that's not scale invariant. Okay, so there's again some special mode that crossed when it crossed when K was equal to K equality. Okay, that special mode there. But let's start again down here at these long wavelength modes. Sorry, short wavelength modes. Those have grown a lot. So sometimes it's useful to have both K and lambda on the same plot. So lambda goes this way, long, short, K goes that way. Okay. So we started our discussion here at the shortest wavelength modes. They get the biggest growth. So this short wavelength mode here is up here somewhere, let's say. And then as I go to longer wavelength modes, I get another dot, 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 where these only differ by a log function. Is what I tried to describe. Remember, they only differ by a log. Does that make sense? I'm just converting these dots into that. And then as I go to longer wavelengths that entered in the matter era, they differ by this big linear factor. So this curve becomes a lot steeper. So is it okay? That's what I'm saying? Okay. So if this one is 10 to the minus 4, this is a K down here, which is equal to our today's Hubble, H naught. So think of that one. Is that one. Say this one is this one, and so on and so forth. Is that okay? Questions about this? Yeah, so then the whole curve, we could just piece this idea together. It's growing as some power law, and then it's flatlining as some logarithm. Okay, and there's a kind of a break at around K equality. Yeah. Okay, and up here somewhere, is like, I don't know, 1 or so. Okay, where things really enter the nonlinear regime. Okay. All right, so because we make measurements today, in some sense, it's really this curve that we map out with our data, right? So then there are data points that have giant error bars down here because it's almost the whole universe. And then our data points get a bit better up here. Okay, something like this. And the consistency of this is what tells us that the idea that it was scale invariant as it enters the horizon, that seems to be what's working. Right? So if we give that thing a big tilt, then we would change the whole shape of this thing, and then we would not fit the data very well. Okay, so it's really that funny, complicated thing that we look at, and we infer the simple thing that it started its life scale invariant. So more questions about this? Okay. So then the punchline, as you can see, is that large scales, this picture self-consistently tells us, has very little fluctuations at the 10 to the minus 4 level. But as you go to smaller and smaller scales, there's huge fluctuations. That's what this initial scale invariance predicts the shape. Okay, and while I'm telling you the data looks like that, okay, And we can, so once again, let's look at one of those simulations and then make some comments about real data. Oh, there we go, step one. Right, so again, we already discussed this, but here it is. On the largest of scales, it's the 10 to the minus 4 level fluctuations. And as we go in, as we zoom in, we're moving to the right on that plot. We're going to smaller wavelengths. And there's much bigger power, much bigger amplitude of these modes on smaller and smaller scales, consistent with this picture. I mean, this is a simulation that using the same rules. So of course we got the same answer. Okay, but just so you can see visually that that is related to that simple plot over there. Okay, and the complications here, the fact that it's some giant mess when I drew a simple curve, right? We should remember that that's because for every K mode here, this is a standard deviation. So you're sampling here, 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 here. You sample, right? So all these different modes have different values, and this is just their standard deviation. And you add up a bazillion of those modes with funny random coefficients, you're going to get a horrible, messy distribution. But qualitatively, it gets has more power on these smaller scales. Okay. So questions about this? If we want to consider data, it's a tricky business. So, you know, you have a tough business to try to compare the output of the simulation, is messy, to real data. But let's say here's real data. So these surveys, and these are real galaxies. And these are slices of what the telescope like looks at a region in the sky and covers it like this, and then turns and look at another region. So it actually only gives us slices of the sky in this flown digital sky survey. So there are just slices here, which will be clear in a minute. And then it's some detailed statistical analysis to check that that matches the simulation or statistically matches that curve I drew on the board over there. But we just have to trust me that that works. Okay, but you can imagine comparing these things directly, right? You start to see the slices here. Okay, so maybe at a glance, it looks a bit like the Millennium simulation. Is that fair to say? The slice the Millennium simulation. And maybe going forward, it's worth to bear this in mind, that as we zoom out, in a way, of course, we're looking backwards in time. And this little movie has fun by pasting on top of it the cosmic microwave background radiation that we're surrounded by. And this is when the universe was 380,000 years old. Okay. So back here, we can directly see essentially the kind of 10 to the minus 4 level fluctuation. Actually, they're a little less when you look at photons. They're closer to 10 minus 5. That's just a detail. But the actual CMB that surrounds us in the very early universe has in it directly the blue and red are qualitatively the same 10 to the minus 4. Okay? That you can check because that's been measured with great detail. And it's from that and more precisely the matter associated with this that evolves into that stuff there. Okay. It's a bit eerie. I sometimes look at this, I think it's a bit eerie that we look out and we surrounded by the baby universe, but it's somehow the way it is, right? We collect it today. Well, we can finish the movie. Yeah, here we go. This is my favorite part of the movie. There are those people staring at the screen. That's a bit like us, I guess. Anyway. All right, so any questions about all this? All right. So this 10 to the minus 4, so in a way, everything fits together once we accept this property, right? So in what sense are we predicting things? So there's something that we're not predicting, which is our initial conditions. The initial conditions were super simple to state. They were that all the modes were 10 to the minus 4 at horizon crossing. That's one number and a trivial dependence on scale. No dependence on scale invariance. And relatedly, it's that the fluctuations in the CMB that I'd like to talk a bit more about, also at that 10 to the minus 4, 10 to the minus 5 level, extremely tiny fluctuations. So we just state that as our universe, and then we evolve the equations. So now in the remaining lectures, we can think about, well, why were those the initial conditions in the first place? But are we okay? Once you accept that initial condition, everything works, more or less. So our task is to think about where these initial conditions, so to speak, came from in the first place. So the fact that things are even close to being the same number, like 10 to the minus 4, the fact that that's near 0, or that the temperature of the CMB is almost the same number, 1 part in 10 to the 5, is itself a kind of strange thing. Okay, so if I talk about CMB, the related statement is that the temperature of the CMB is about the sort of mean value. That's the sort of, let's say today, that's the 2.7 Kelvin. And then you can also talk about fluctuations in that, delta T over T bar, I guess. So yeah, this could be a function of position. Okay, so this little fluctuation here is about 10 to the minus 5, actually, not quite 10 to the minus 4. Same idea. So I would like to say that this is actually the fact that it's almost the same. So literally, you collect photons from that direction in the sky, you collect photons from that direction in the sky, and they're almost exactly the same temperature, right? So things being at a common temperature, right, we might say is a pretty standard thing because of the laws of thermodynamics, right? Things like coming to the same temperature if you put them in contact with one another. Our universe today is very big, so it seems a little odd. Now we might say, again, well, what happened in the early universe, right? So as you go back in time, things were somehow very close together as you go back towards the Big Bang. So it's like what I said before, you've got to worry about two things that are both getting small, right? If you want to know why that part of the CMB and that part of the CMB are more or less the same temperature, you say, well, in the past they were super close, so things nearby can come to the same temperature, right? I can, if this, this is hot and this is cold, I let them go, they can come to a common temperature. But the same thing that says, well, I'm in the early universe, so they're nearby one another, you're playing a double game because, yeah, but the early universe, let's say the universe was 1 second old, where everything was close to one another. Well, they only had 1 second to come to the same temperature, right? So you're appealing to their closeness, but the penalty is that you're appealing to a very short amount of time for that thermalization process to happen. So you wonder, well, what wins? Okay, do I really have enough time? Because both of these things are going to 0 as I head towards the Big Bang, the size and the time that they could have equilibrated. All right. So we can talk about this precisely. So I want to say something about the causal structure of the universe. Okay, so we'll start with our usual metric. Our metric. And it's going to be useful to us to define a different time variable. Okay, so I'm going to define a new variable called conformal time. So I'm going to write d eta, yeah, as dt over a. And if I do that here, right, or the other way around, dt equals a d eta, it will allow me to pull out the a squared in front. So this eta is called conformal time. So we're going to do that. I'm allowed to. I guess I can write a squared of eta because I'm changing my clock from t to eta. And then I can write this thing. So with respect to this conformal time defined by this, the metric looks extra nice, you could say, because apart from a prefactor out front, this looks like the flat space metric. Right? Looks like flat space time, except there's a prefactor. So it knows that it's the same universe. Okay? But this is super duper nice because if we consider the behavior of light, right, light has ds squared equals to 0. So at best, if the system is going to equilibrate, it has to send signals for, say, if there's a hot bit and a cold bit, it could send signals at best at the speed of light to equilibrate. So light is, of course, the fastest things could move at. That, it just means that this thing here, I don't even have to worry about the prefactor. Right? It's just the statement that d eta squared equals this usual thing, as in flat space. Okay. If we pay attention to just motion along the x-axis, let's say I just think about the photons that come from that side to the positive x-axis versus the photons that come from the negative x-axis. Those photons come to me from the CMB. Then we can just write, and simplify our life, you know, d eta is just plus or minus dx, like this. Okay. Super simple. Light's just traveling at speed c is equal to 1 with respect to conformal time. Okay, so this allows us to start talking about the causal structure very a little easier. Okay, so I'm going to put eta going up. A little discussion about that earlier. Time will go up. And x, we're just going to focus on the x-axis here. Okay, so let's say we're here, right, and we're collecting photons from the CMB, from that side and that side. Don't worry about the rest of the CMB with the y and z directions. So because we have this, light, as it is in flat space, just moves at 45 degrees in this space-time diagram. So this is how light gets to us. Okay. This is 45 degrees. 45 degrees. Usual stuff. Okay. And now there's some time in the past when the universe was 380,000 years was t. It doesn't mean that eta was 380,000 years. It will not be eta of 380,000, but t of 380,000 was when the CMB was emitted. So I'll just mark it here. Call this CMB. It's t, not eta, is 380,000 years. Okay, and so as you saw in the movie, there's this two spheres surrounding us. In some sense, is the CMB. Okay, so there are photons from that come to us on that side, photons from that come to us, both sides there and there. And the CMB has its own past, the first 380,000 years, according to regular time. So I should keep extending this. I can draw this, and I can draw this. And this region here, this is the past light cone of the electrons and so on that make up, that are in the universe, this plasma, that ultimately emit photons that cause the CMB. So this is their past light cone. Okay? So over here, our statement, right, is that the temperature here, we can call it, I don't know, T1, or maybe I'll call this TA and TB. This is the A part of the universe and the B part of the universe. Our statement here is that to very, very high precision, whatever moment in time you consider, right, TA is very, very close to TB, right, to 1 pi 10 to the 5. Now, a question then basically is, how do I have to think about extending this past light cone. I just stopped somewhere. I should keep going back to the Big Bang, let's say. And so since I haven't calculated eta yet, I haven't done an integral, we're going to do that in a minute if there's time, right? There's something that could happen, right? It could happen that the Big Bang is here. That's true, with a little wobbly line is the Big Bang. Okay? Maybe that's what happens. We have to do a calculation that I just stopped it there. And if that's the case, then the past light cone here and the past light cone there are separate. So this would mean that there's no way that there's a causal process that could force that temperature and that temperature to be the same. Does that make sense? So this is one possibility. We have to do a calculation. It could be that when we do a calculation to find out when the Big Bang is, so I have to find out when is t equals 0 and convert that to eta. That requires an integral. Maybe we find, I didn't leave myself enough room, but yeah, well, we can do it, that this continues down and there's a point at which they cross. So maybe here's the Big Bang. Okay, and then at least there is some region here, the way I drew it, where they have some intersection. Okay, so maybe that's where the Big Bang occurs, in which case they have a common causal past. Okay, I drew it as a little region. Maybe it's a very big region because I had to got stuck by the board. You see what I'm saying? Maybe t equals 0 corresponds to eta of minus infinity. We have to do an integral, in which case they would have a wonderfully big common path, in which case they could come to the same temperature. Okay, so it could be where the Big Bang singularity is here, like I drew a second ago, and then we're in trouble from causality. Or it could be like this, and we're okay from causality. Does that make sense? So we have to do a calculation to figure out which it is. All right. So let me I'm going to mark some points on this. The risk of giving it away, I'm going to draw this curve, this plot. Okay. So everything here is 45 degrees, right? So I want to compute, for example, this time interval in eta. So maybe we could call this eta r. That's the eta at which the universe, the first moment it got filled with radiation, which for our purpose in this course so far has been at the Big Bang, it just started with radiation. Okay, but that we could say is the time at which you were radiation or the time at which you hit the Big Bang singularity. Is that all right? And this moment here would be eta CMB. Okay. And then we can also go, well, we can also go all the way up to, I guess, eta today. Okay. And so that means this gap here is eta naught minus eta CMB. Okay. So eta CMB, eta radiation. This is eta CMB minus eta radiation. Okay. Anyway, just a name for this interval versus this interval. So I hope you can see this question of causality is a question of which of these two intervals is bigger. Okay. If these two intervals are exactly the same length, these triangles meet at a point. If, as I've drawn it here, it's the case in which this interval is less than that interval, then we're in trouble. Or it might be that this interval is bigger and I didn't draw it right, and then we're okay. So we literally want to compare that interval to that interval. That tells us whether the triangles overlap or not. Okay. So we just have to do an integral of this thing. Hopefully we have time. Any questions about this? So let's start. Yeah. That would be an interesting coincidence, I guess. Be a bit strange. We're not going to get that, but I guess that would be strange. Okay. So I can write, remember I wrote d eta is dt over a. I'm going to turn that into an integral, and I just have to think about my endpoints of integration, basically. So I could write this eta, say CMB, minus eta radiation, that first time interval, the red interval, if you like, is then the integral in time dt over a. I can make these, yeah, that's fine. And in regular time, I'm starting at the Big Bang. So that was what we usually call t is equal to 0. That's our convention normally, up to t CMB. Everyone okay with that? Big Bang to t CMB. And this eta r here, well, you could put eta r to 0 if you like. Okay, I just keep it in as a reference. We get to choose our 0 point of time, however we like. Okay, so I got to do this integral here. So this is the integral from 0 to t equality. Okay, well, we're going to approximate this thing. Okay, so the annoying thing is that for the first 47,000 years, we're in radiation. A is t to the 1/2. And then we're in matter up to here, or up to very late times, to 10 billion years, where it's t to the 2/3. So we can break up our integral. Okay, this doesn't matter too much, but we might as well state it properly. So this is going to be something like dt. I could write A equality t over t equality to the 1/2. See, in the radiation here, it's t to the 1/2. And I forced the constant proportionality to be correct. When t equals t equality, A is A equality. So that's like half this integral, roughly speaking. And then there's the other half from t equality to t CMB, where I could use the same convention, t over t equality to the 2/3. That's because we entered the matter era. Okay, so you see these are sort of some elementary integrals we can do. But first of all, what's very important is to look at this first integral. This first integral, we're integrating all the way back to the Big Bang at t is equal to 0, a of 0. And you see that a is proportional to root t. So if the integral of 1 over root t, and we integrate to 0. So this integrand diverges as t goes to 0. Okay, but what can we say about this integral? Is this a bad integral, bad divergence, or a nice divergence? Integrating 1 over root t to t of 0. What kind of divergence is that? Is this infinity? Good divergence. Why is it good? I guess let me find out. Yeah. This is an integrable singularity. It's very important that it's t to the 1/2. In fact, if it's a power, that power just needs to be less than 1. And then it's an integrable singularity. Right? If this was 1 over, I don't know, t squared or something, you would be in trouble. It would diverge. Which, well, I say trouble, actually, it would be very good news from the point of view of causality. It'd mean that I should somehow be pushing there's an infinite piece here that I've not captured. So we might push that into the past and then they can overlap. But that's not what's happening here. This is a finite answer. Okay, the specific numbers don't matter too much. I guess right on the board. Well, the specific numbers actually do matter a bit. Okay, anyway, you can do the integral. And every number here we know, right? T equality is 47,000 years. T C and B is 380,000 years. A equality is 1 over 3,600. And that's all that's there. Okay, we've specified all those numbers in the course. Okay, so you just plug them in and you'll get a number that's about 8 times 10 to the 8 years. That's a bit big. It might have sounds a little big. It has the threat of diverging, but doesn't quite diverge. So you see, maybe it's not so shocking that we got a big answer, but it is finite. Big, I mean that this number is bigger than the 380,000 years, which is what regular time says that this event happens at. So conformal time, somehow 800 million years has elapsed from there to there. That's a bit big. Well, we're going to see it's not as big as this. That's the next. We could then do the next little calculation. We have to do the second interval. Okay. So e to 0 minus e to CMB, right? The second interval now. We could write that as T CMB. Yeah, to T matter vacuum equality. So you have a matter era from here to 10 billion years, and then a little bit of dark energy. So I also have to split the integral. Well, these are just approximations because there's no sharp transitions, but this is good enough. That's the matter part, and then there's the final dark energy bit to today. And in dark energy, if it's a cosmology constant, things are growing as an exponential. Okay, there's an exponential growth in the dark energy era. Okay, so these are, again, two elementary integrals. I'm not going to write the value on the board. Is that okay? But we know all the numbers, right? A equality, T equality, so on. T matter vacuum equality is 10 billion years. We know all the numbers. Okay, this is basically today's Hubble value. Is that all right? So you can just do the integral. And this one comes out to about 5 by 10 to the 10 years. Yeah, 50 billion years. So again, a bit longer than regular time. Okay, so it's almost a factor of 100 bigger. We went to conformal time, and this gap here is, I don't know, it's about 60. This is about 60 times bigger than that number. Okay, so there's a 60 to 1. So I should really cut this thing off. You know, my singularity is like here somewhere. So I was drawing it properly. Is that okay? Let me not bother drawing that, but it's qualitatively this picture. But there is quite a big discrepancy. So there is no common causal past in the standard cosmology. Okay, they're a factor of 60 separated, actually, roughly. And this scenario only gets worse if you were to go to even earlier stuff. Like, for example, the primordial elements. We see 25% helium there and 25% helium there. But they were created when the universe was a second old. Right? So I should then, for Big Bang nuclear synthesis, I should draw a little, its past light cone was down here somewhere because it was created very early. And it's totally different than the past light cone of the Big Bang nuclear synthesis on the other side of the sky. So whatever you look at, it only gets worse. But we'll just use CMB as a good thing to think about, because we see it very directly. Okay. So, all right, so we have this picture. So they have no No common causal paths. Okay, what time do we have? All right, I guess we're running out of time, so we can pick it up next time. But basically, what we wish to discuss then is the proposal for inflation. In short, is to tack on a new era before the radiation era. And it will tack on an era which pushes this singularity or way back. So they'll easily have a common path. Okay, that's one of many nice things that it does. As a side bonus, the scale invariant fluctuations will also show up. Any questions? All right, thank you.